Greetings, Earthlings! Before we start exploring, don't forget to like, comment, and subscribe, wherever you're listening. It helps more people find the show and supports our mission of making science accessible to everyone. You're here with DJ Stellar Cloud. Thank you for tuning in. Welcome back to the Exploring Your Universe radio show. Exploring Your Universe is UCLA and LA County's largest science fair. Every year we have over 500 volunteers. If you're listening, you could easily be one. And over 12,000 visitors. If you're listening, you probably are one. This year, Exploring Your Universe will take place on November 2nd from 12 to 5 p.m. on the UCLA Court of Sciences. This is DJ Stellar Cloud and
DJ Stats Sleuth.
DJ Stats Sleuth, aka Jaahnavee Venkatraman, is a fourth-year PhD student in the Earth, Planetary, and Space Sciences department here at UCLA. You may recognize her from a previous episode back when we were live on UCLAradio.com. If you haven't listened, I recommend that you look through our YouTube playlist and give that episode a listen. It's one of my favorites. During that episode, we heard a lot about her journey from Illinois to India and eventually to UCLA. But we didn't get to hear anything about what she did at UCLA because we talked so much we ran out of time. So today, let's hear what she does at UCLA.
Hello. Thank you for having me again.
Yes, thank you for coming.
Yeah. So, where to start? I am a fourth-year PhD student, as you mentioned, and I'm happy to be here to talk about my research. I am a planetary science major, and, EPSS has a bunch of different majors in the department, which is really nice because we get to sort of make it a little interdisciplinary. So I do a mix of, I would say, astrophysics and planetary geology and some geophysics, and it's just a very fun mix of things that I get to do. My focus is the lunar and Martian surfaces, but I'm, hoping one day that I can move beyond that and do other sort of non-solid airless body surfaces.
What's funny is I think these are the two places that people most want to visit.
It's true, yeah.
So that's kind of exciting. You're very involved with the mission side of everything, which is when people actually go visit or send payloads to places.
Yeah, it's very marketable research.
Absolutely.
Yeah.
But you want to move on to different airless bodies? Sorry, what did you say?
I said I want to move on to non-airless bodies. So I guess Mars is technically less airless, and by airless I mean either little to no atmosphere or just an atmosphere that is, a lot less dense than Earth's atmosphere. Yeah. So Mars technically would be considered like a semi-airless body because a lot of the processes that are preserved on the moon, for example, because there's no atmosphere and there are no tectonics and things like that, also are preserved on Mars. And it allows us to sort of go back further into its geologic history than we are able to on Earth, for instance.
On Earth, everything is always getting moved and blown up and all that. And
yeah,
you can't really see a lot of the geologic history, but I guess when there is no atmosphere, nothing's rotting or oxidizing.
Yeah, usually it's the lack of an atmosphere on the moon, for example. There are no hydrological cycles, so there really is no no water cycle. There's no CO2 cycle. There are no tectonics, volcanism. So if you had an atmosphere, for example, with outgassing from volcanism, that would be an indication that there are a lot of things happening on the surface. So an atmosphere is basically indication that there's a lot of stuff happening. It's not necessarily directly that the atmosphere is raining out on the surface, which is one of the things, but it could also be an indication of other things going on at the surface that would erase prior histories.
Okay, yeah, that makes sense, because your atmosphere is evidence that something else is pumping out gas to become the atmosphere. So beyond this is breathable air, there's so much you can learn about what's actually happening on the surface of that body. Okay, cool. So eventually you want to move on to things that have atmospheres.
Yeah,
Any reason why?
I think it would just be a bunch of different physics that I've never tackled, and I think it would be really interesting. But it is something that I don't have a lot of expertise with, so it would just be for fun, for me to explore different areas of planetary physics, essentially.
I guess some personal bias, the exoplanet atmospheres community is booming and extremely competitive because of the search for biosignatures. And then, of course, for anyone listening, most atmospheres that we know about are nothing like Earth's atmospheres. Yeah. We're talking weird stuff like the raining of diamonds and the air is thick carbon dioxide or something like that. But I do understand the desire to learn about all different kinds of planetary bodies, because it sounds like the moon and Mars have a lot of similarities.
Yeah, they do have a lot of similarities, and that's why it's so nice to study both of them in parallel, because I feel like if you start on Mars, you can apply a lot of the physics of Mars to the moon and vice versa.
I see.
And so I started on the moon and with lunar surface geology, and then I applied for an internship at JPL to do Martian surface geology, and it translated really well, actually. I think that the moon gave me a good strong background in impact processes. And
impact processes are like craters and asteroids hitting.
Yeah.
Okay.
So the moon went through this period, if you believe it, called the late heavy bombardment, which
That's
there's
so funny.
some people don't believe in it, and it's mostly geochemists, I think.
Okay. I do know about this. There's a lot of arguing of several different camps about whether or not planetary bodies have been hit by other planetary bodies and when this happened.
Yeah.
Okay.
And the time period, there's like a window of, it's like a few 100 million years or something like that, and so it's a really, really long window.
But on a planetary scale, that's a fairly normal time.
It's a fairly normal time scale, yeah. But I mean, we think that it happened because that's how we think the moon initially formed from a Mars-sized object that impacted Earth, and then broke it off. And the moon then went through this late heavy bombardment period where most of its surface features that we see today are impact craters from that time that have then been sort of impacted, overlaid with more impacts. And
I mean, this is why people think the moon is made of cheese, because it has all these holes. Like, cheese has holes.
Yeah. One really cool thing, actually, that it's sort of a fun fact that not a lot of people know, which surprised me when I started studying the moon, is the dark patch of the moon is called the lunar mare, and the light patch is called the lunar highlands, and there's a huge difference in composition between the two, because the lunar mare were volcanic flows and basically big magma oceans.
Flows
that,
is F-L-O-E-S?
F-L-O-W-S.
Oh, it is F-L-O-W-S.
Yeah.
What is F-L-O-E? That's another thing. Okay, I'll look that up later.
I don't know.
Anyway, volcanic flows. This is actual lava?
Yeah, so this is actual lava.
The moon had lava.
Yeah, and so we think that it was when it was cooling down still. Okay. So the moon, actually, the whole thing is a magma ocean. It's just a hot rock that cooled, essentially.
I can't believe I've never known this before. That's really funny.
So the highlands material technically is also a magma ocean that cooled.
Okay, like pumice stones or?
It's ferrous anorthosite, and anorthosite is this like light-toned material. So that's why the whole moon is very, very gray and light-toned.
And ferrous is magnetic.
Ferrous is iron. Okay. And there's a lot of aluminum, magnesium in these highland regions.
Interesting.
So yeah, I mean, the lunar mare is a different composition from the lunar highlands, and it's an interesting fact that I feel like a lot of people don't know. And so their process of formation was very different. So the moon is actually entirely a magma ocean that just cooled. It's just a giant rock that was shaved off of the Earth and then cooled. And once it cooled, about I think like a few million years ago, the mare formed, which was extrusive volcanism, and that basically means that they're traditional volcanoes like we see on Earth.
Cinder cone, shield.
Yeah, and so that's the stuff that produces the pumice and the volcanic ash and what we're more familiar with on Earth. But the ferrous anorthosite material that forms the highlands, that's that light, really light gray that you see on the moon, is not really prevalent on Earth that extensively.
Can't find that here at all.
I think you can, but I don't think it's easy to find. And I think that that's because of all of the reworking that's happened on Earth. So Earth also had a magma ocean because we obviously have a lot of tectonics, and tectonics are facilitated by the fact that we have this fluid magma that's able to move the surface of the Earth, right?
Yeah, this is the mantle.
This is the mantle, yeah. So we did have, the Earth cooled similarly to the moon. So we suspect that there was a magma ocean on Earth as well, but it's been reworked so heavily because of how much geologic activity there is that I would suspect that the pristine nature of the anorthosite on the moon is not really prevalent.
Okay, the word you're saying, anorthosite.
Yes.
Okay, ferrous anorthosite.
Yes.
If I've learned anything today, it's ferrous anorthosite. I'm going to start saying that everywhere, and if I ever need to get you jewelry, I'm going to be like, where do I find some ferrous anorthosite?
The cool thing is it's abbreviated in a lot of papers because it's a mouthful, and it's abbreviated as FAN, F-A-N.
Oh, I like that. Okay, that's cool. Okay, so this is part of the highlands, and then the mare was the magma ocean. No, it's all magma ocean.
The highlands is all magma ocean. That was then covered by extrusive volcanic lava flows, basically. Okay. That is the mare.
Cool. Okay, so what do you do with this knowledge? Like, what is the point of learning the different rocks that make up the surfaces.
Yeah, so, I mean, a big part of it is understanding the formation mechanism of both the surfaces, and then it also gives us sort of a time scale as to, you know, which formed first, which formed later. Did Earth go through similar processes that the moon did to form and cool? So what I was talking about, you know, with the magma ocean. What I specifically do is I try to characterize the surface of the moon. And so it's really helpful for manned missions, for example. So for the upcoming Artemis missions, our knowledge pool that we have of what the surface looks like is so much better than what we had during the Apollo era.
Certainly.
And so, for instance, in the first paper that I published, oh
my god, look at this multi-papered queen. What the heck?
Multi-papered queen.
In my first paper, in my 16th paper.
Oh, I wish 16. That's how you know that I'm too good for a postdoc, is if I have 16 papers.
My advisor and I were talking, and he's like, it would be nice if you had a paper before you defended your thesis. And I'm like, yeah, it would be.
But you have two.
So I have a research note, which is not peer reviewed, and then I have a peer reviewed paper from an REU that I started like way before grad school. Yeah.
That counts?
It counts.
Yeah. My only first author publication is this one, and I published it in grad school, but most of the research was done when I was an undergrad, actually, and then in between. When
There's
I took
a few of us like that, actually.
Yeah. And it's very common for, I feel like if you're coming into grad school, it's expected that you have research or a publication that would be amazing and ideal to get you ahead of the curve. But typically the way that happens is if you do research as an undergrad and then publish it as an undergrad.
Yeah.
And so it's not uncommon to have a project coming in, especially if it's unpublished.
Yeah.
Or like, you know, if it is published, then you just build off of that and it becomes a lot easier to form that first project.
So did you come in with this project?
I did come in with this project.
Okay. So you had this from JPL.
The JPL one was the Mars project. So I actually have 3 different projects that I work on. So
wow. The juggling,
it's hard sometimes because I have to turn on and off my Mars and moon brain.
Oh.
And it is, even though it's similar, it is different in a lot of ways. So
I mean, even just the way people store data sets is going to be different.
And exactly. Actually very different.
Yeah.
And annoyingly so. But I think the lunar people who store data are very, very good at it. And they've really compiled it nicely in a database that is very easy to digest. So I appreciate that. Makes lunar science more fun. But my 3 projects, so my first one is looking at the surface of the moon and characterizing this thing called rock abundance.
Okay.
And that basically is just a fancy way of saying how many big boulders that are larger than a meter in diameter are there on the surface.
Oh, so the surface is not intact.
It is not intact in the sense that it's constantly being impacted, and so you have constant regolith development on the moon.
This is impacted by other meteors and asteroids? Okay.
Yeah, so that sort of dusty material, like if you ever...
moon dust.
Yeah, moon dust. I don't know if the listeners have ever seen moon dust in a museum, or simulant, which is basically sort of ground up concrete, essentially, is a really good fake moon dust that we use for education as an educational tool.
Well, even the picture of the astronaut's footprint is clearly in some kind of sand. It's like you went to the beach.
Yeah, and it's really fine, and it can get in your spacesuit, and it's just really, it's actually quite dangerous. But
oh, why is it dangerous?
Because if it gets in your suit, it can impact the
breathing.
Yeah, the vacuum like seal, basically.
Oh,
yeah.
I've got sand in my breathing too.
So it can get in places you don't want it.
It's like beach sand.
It's like beach sand, yeah. And so imagine ground up concrete, and that gets thicker and thicker if you have, for example, a bowl of this ground up concrete and you have rock beneath it and you have stuff hitting it, then that rock is going to break up and add to your surface material. So that fine layer gets thicker and thicker. But at the same time, you have simultaneously a compaction process. So all of this regolith is being broken up, but also pushed down.
Okay.
So you're forming rock and you're forming regolith. So it's a very complicated process that people have tried to model, but it's quite difficult to do it.
My cat is really excited by this podcast. We're recording this episode in my home because our regular studio is currently under construction, and I don't know if the sounds of the cat drinking water are getting it or anything, but she's a really good companion.
She actually looks a little bit like Moondust.
She looks a lot like Moon does.
Yeah.
We'll have to upload a photo of her at some point. So you did come in with this moon project. How did you get assigned to this moon project?
That's a good question. So I actually... and I think I maybe touched on this a little bit in the previous episode, but I started off as a statistics major.
Yes.
And my background...
Stats Sleuth.
Yeah, exactly. And so I started off with stats and machine learning, and that's my background. And I did a minor in geophysics and space physics because I went to school in India. I think I had such a strong background in physics that I really missed, and I didn't realize how much I actually liked space before I didn't have it anymore. And I was like, oh, okay, I think I kind of want to... I don't want to major in it because I don't think it's what I want to do, but I'm going to minor in it because it's easy to just add these courses on. It's just a lighter load. And that's when I met my current advisor, who essentially was such a good advisor that I was convinced into doing the PhD.
Really?
Because he made me enjoy this research so much and sort of showed me the possibilities of pursuing this kind of a career. And I think...
This is Dave Page?
This is Dave Page, yeah.
Dave Page is an extremely charismatic man. I've had lunch with him a few times, and you just, like, can't be around him without laughing. Like, I don't even know why I'm laughing. Like, he's not even telling jokes. He's just being himself, but I'm just excited to be there. So I totally get it. I would also be like, okay, I'll do this for 6 years. I'll hang out and vibe for 6 years.
And the great thing about him is he has not lost his childlike spirit.
Yeah.
And I think that's what I strive to be when I'm his age. You know, he's in his mid-60s, I think, and he does not... Other than his gray hair, I don't think you could tell that he's in his mid-60s. Because the way that we do field work, when it's, you know, we're in the rugged outdoors, we're camping, lifting heavy equipment, he has a truck, like, he's helping us lift stuff. It's just, and he subsists on, like, an apple and some spaghetti, you know?
And he's in a rock band.
Yeah, he is in a rock band.
I totally strive to be like him when I'm older and have, like, such a fruitful research group, because your group is kind of large. You've had quite a few grad students.
Yeah.
And undergrads.
And undergrads. We have a lot of undergrads and grad students and a lot of staff because he likes to go on these side quests quite a bit. Okay. Because he's so good at instrument design and things that are energy related, things that are like just, you know, with up and coming technology being so in the know, he's very good at this stuff and very good at learning on the job. And so he comes up with all of these, like I said, side quests.
Yeah.
Where, for example, there was this one project where he wanted me to build a sort of at-home ground-penetrating radar, which is an instrument that he has on Mars, and it's a much larger version of it.
Wait. Okay. How are you just going to, like, build your own radar?
Exactly.
He's just like, Jaahnavee, DJ Stats Sleuth, could you go build a radar for me really quick? It has to go through, like, 10 meters of straight rock and concrete. Okay.
And it's funny because I feel like he'll go to bed and then in the middle of the night he'll have a dream and then text me and be like, Jaahnavee, I just had this thought about the small radar that you're building, and it'll be a completely valid thought.
What?
Yeah.
Okay, this is actually how I solved my first Fourier transform. I don't know so a Fourier transform is how we convert radio waves into sound. So if you're listening on the radio, which I don't know how you would be doing, your radio is doing some kind of Fourier transform to change whatever electrical signals I'm sending it and make it something that's actually intelligible. And so when you are a physics major, as, like, you know, a small 19-year-old or whatever, you have to do this math by hand, and it's a really complicated integral, and the first one that I solved, I actually also solved in a dream. So I'm on my way to being Dave Page.
Oh, yeah.
I'll have to pick up a few more side quests on the way.
You basically have to get distracted at every turn and then come up somehow with a completely plausible answer for the thing that you were.
Okay.
Yeah.
Well, I've done the first part. I can get distracted at every turn. Because how did you get assigned the moon project?
Oh, yeah. Well, so I met Dave in
when you were minoring it.
Yeah, in a planetary surfaces class that I was taking, and we ended up doing this, like, final project basically where he was like, come up with anything that's relevant to the class, anything under the sun. I was like, okay, I kind of want to mash my statistics with geophysics and see if this is, you know, a viable project that I can come up with. And I realized that there was a lot of current research on depth to diameter ratios of impact craters on the moon. And so basically it's just people studying how the sizes of impact craters change as you move to different latitudes and longitudes, and what that can tell us about the moon's geologic history, which seems like it wouldn't tell you much, but it actually does tell you a lot, especially if you're interested in what we're interested in, which is ice. And so that's how I got started on this, because I came up with this idea and he was like, you know what, I have a grad student already working on this, so you should just join him.
Wait, that's crazy. So you accidentally came up with a real project that was already existing in his group at that time.
Yeah.
Wait.
And so he said, you should just work with him. And I said, that would be amazing. I would love to do this. This was Lior, actually, who also is very interested in machine learning and statistics. And so it was a match made in heaven. He was such a great mentor.
Okay.
What an incredibly genius man.
Did he graduate?
He did graduate, He graduated in, I think, 3 years.
What?
Yeah.
From PhD school?
From a PhD, yeah.
Oh.
With a wife and a kid.
Okay.
A newborn baby.
Lior is that Asian cousin I am always going to be compared to. Already graduated by this time, married with children.
I know. He is, and I'm so lucky to have been mentored by him, because I think that really sort of added to how excited I was to do something like this. I think it's really easy to get an advisor or a mentor that is completely disinterested in what you want to do in the future. And I think that was not Lior. Lior was fully invested in, helping me, guiding me through the process.
For his short time here, too.
I know. So yeah, and then I did this project and it was successful, and I got a publication out of it, which was amazing.
Wonderful.
And I got to present it at a very big conference in our field, which is the Lunar Planetary Science Conference that happens in Texas.
People are always telling me about this. I'm not invited, but
well, you can go, because we have outer bodies, and you can maybe get into the asteroid world.
We're gonna let DJ Emmers do the asteroid world stuff. That's the desk next to me.
Yeah.
Okay, so that's how you got your moon project, and then you got assigned build a ground penetrating radar.
That was one of my many side quests.
Okay, so this is not even like a main project.
No, it's not a main project.
Side dish to the side dish, dipping sauce.
Yeah, and that's another great thing I think about my grad school experience is, even though I think it might take me longer than most people to graduate, I've done so many things that I feel like I have developed skill sets that I don't even think I realize I have until someone gives me something to do and I'm like, wait, actually, I know how to do that.
I feel very similarly.
That's good.
Yeah.
Yeah.
I mean, all of my side quests are running Exploring Your Universe and the Exploring Your Universe radio show. But these are cool side quests to have as well.
Well, you're a professional DJ now.
I know, isn't that funny?
Yeah. So if you wanted to work at NPR.
Oh my gosh. The UCLA radio students who go work at NPR are so good at what they do that they just get sniped while they're still in undergrad.
Yeah.
It's kind of insane. I have a lot of respect for them. Okay, I really want to know how you built the ground penetrating radar. I've never done anything like this before. I'm not an engineer.
So, spoiler, I didn't successfully do it.
Okay, but you tried your best.
I did try it, and the reason that he gave me that project was because I had a brief hiatus in between undergrad and grad school where I worked at this consulting company that specialized in aerospace and GPS and defense and stuff.
This is Booz Allen Hamilton.
This is Booz Allen Hamilton. Yeah, free plug.
Love them. No, I mean, the people who work there always go back to undergrad schools and talk to the students about what they could possibly do in consulting, because consulting is such a
broad.
It's broad, but it's also mysterious.
Yes, it is. It's a black box kind of.
Yes.
And it is what you make of it, which is very, I didn't really know what consulting was, honestly, before I got into it. They were just like, oh, you have a geophysics and stats background and you're a perfect fit. And you're going to be working on GPS chips. So I started off, there's this first 6-month period where you're basically onboarding, and you aren't assigned a project, but you're what consultants call beached. So
I know about this.
Yeah.
Because I know somebody who got beached and then just got fired because they were beached for too long.
Oh, that's horrible.
Oh, it's okay, because he's a questionable person, so it was fine. We didn't feel bad for him. This is funny. But I would feel bad for you if this happened to you.
Yeah, and so, everyone starts out for the first 6 months, and then you're supposed to be proactive and find a project, which is really stressful.
Yeah.
But thankfully, I think Booz Allen Hamilton is actually a really good place to work. I'm not just saying that.
That's great.
And it's because I think the people were really good, and so they tried to keep me focused on getting a project before I got laid off. So the project that I first got on was building a GPS receiver and transmitter using software-defined radio. So essentially when you think of a radio...
Oh my god, this is my job.
Oh, no, yeah. Well, you
that's
do.
Funny.
Yeah.
Okay.
So when you, I mean, I don't know if you've talked about it on the podcast before.
No, I hardly talk about my research on the podcast.
I know, we need to talk about your research.
That'll be a future episode. Yeah. DJ Emmers has agreed to interview me for a future episode.
Ooh, can I be a +1?
Oh my god, yeah, of course.
So basically, for the listeners, you know, when you think of a radio, it's all built in hardware. So you have an antenna that's receiving and sending signals. Mm-hmm. It's all the hardware is doing all the work to take in the electromagnetic signal and then amplify it and, you know, send it out as, like you said, intelligible sound. Yeah. What I did was use a little bit of hardware that is really modifiable using software. And so other than the antenna, everything else was specified in the software. And so you can change how much you're amplifying your signal. You can change like the frequencies that you're receiving and transmitting. And all of that is just done on your computer. Yeah. Basically in these blocks that were built in C++. Nice. And so because I had experience doing this, Dave sort of threw this project at me and he was like, well, you've done it with the GPS frequencies. Now just change it to radio frequency. It's slightly different. Okay. But I tried doing it and I wasn't successful, but that's the reason that I landed up with that project.
Okay. Because you sort of already had a background in ground penetrating radar.
Yeah.
It's just like when LinkedIn texts you and they're like, your background in unemployed. Okay, no, I got your background in undecided, because I was an undecided major when I first came into college, and it was like fill in the blank.
Me too.
Nice.
Yeah.
We have a lot in common.
We do have a lot in common.
Okay. Other than the moon, you also work on Mars.
I do.
There are spiders on Mars.
There are, as David Bowie famously said.
Wait, what?
It's his album called Spiders on Mars.
Wait.
Well, actually, no, the band was... I think it's the album, actually.
I'm kind of, like, annoyed now with myself that I didn't know this was a David Bowie album. Because I did listen to your entire talk on Spiders on Mars. I tried my best to pay attention. My attention span's terrible, but I remember the Spiders on Mars thing.
Yeah. It's I made a David Bowie joke at the beginning because it's like, how can you not, you know?
Wait, that's so embarrassing that I forgot. Sorry.
That's okay.
I was there and I was trying my best.
Well, it was a long colloquium or seminar. But basically what I do is I look at these features that are colloquially called spiders, but in the science world, they're called areniforms. Okay. And areni basically translates to spider. Yeah. And they're these formations that they have a central pit, and then they have these like spidery dendritic troughs that radially project outwards from that central pit. And giving them that sort of spider-like look, and they collect on the south pole of Mars, where there is this thing called the South Polar Layered Deposit. And that is essentially, if you think of the ice caps on Earth and how they grow and shrink with the seasons, it's very similar on Mars, but instead of a water cycle with water caps, we have a CO2 cycle with CO2 ice caps on Mars.
I forgot that ice can be made up of many different things.
Yeah.
You got water, CO2, methane.
Methane, you can have methane ice, yeah. And there is a little bit of methane on Mars, but not a lot. Okay. And people are still trying to figure out whether or not it's cow farts.
But, I know, I hear about this all day long. Yeah. My inbox is flooded with this.
Where is the methane from?
Like, I don't know. This is not my job. It's actually your job.
Yeah, I look at these spiders, and the way that we think that they form is essentially CO2 ice forms slabs at the South Pole, and we think that the way that this ice behaves is it sublimates basally, and so that means from the base of the slab of ice upwards. Okay. So the top doesn't sublimate, and again, everything what I mean by sublimation is, if you've ever seen naphthalene balls that you put in your closet to like ward away the insects, those are one of the handful of things on Earth that sublimate, which is that they transform directly from a solid to a gas. There's no liquid phase. And the reason that a lot of the common materials that usually have a liquid phase on Earth don't have that on Mars is because of the temperature and pressure conditions there. And so because you have such low pressure, you just have this direct phase change from gas to solid or solid to gas. So basically this ice starts to sublimate at the bottom, and you have all of this gas buildup at the bottom of a slab. But if you think about it, it's all getting trapped in this sort of upper
under
layer.
its own ice.
Exactly.
Okay.
And so it builds up and finds a weak point in the ice and eventually bursts through, like a geyser almost in Yellowstone.
Oh, okay.
And when it bursts through, it pulls up material from beneath the ice that's all basically sand, and it pulls it up in this radial spider-like fashion. And so when the ice sublimates, you can see these spiders left behind.
It's really funny to me that, like, this whole ice made out of CO2 or whatever is, like, going through it, and then it's like, you're coming with me.
Yeah.
Since I'm blowing up, you also have to go. And then the Mars dust is like, oops, now I'm a spider. Okay, whatever.
And the interesting thing is we don't really know a lot about how they, like, when they formed, how often they form. If they're currently forming, like, we don't know if they're just getting covered by the dust and then re-exposed, or if they're actively getting deeper. There's really not a lot of clear data to be able to figure this out. And so we sort of, my job is to look at the thermal signature that we see from these spiders from orbital data, which is basically we have a spacecraft that is orbiting Mars, and there is an infrared camera on there, similar to how I gauge whether or not there's rock with infrared on the moon.
Yeah.
I'm using infrared on Mars to look at the dust. So this will sort of tell us, you know, how much dust is there. Is it dusty just where the spiders are? Is it dusty everywhere? Where is the dust coming from? So that sort of stuff.
What is the name of the machine that looks at Mars?
Themis.
Oh, okay.
Yeah.
So you got
Themis
the minor...
and TESS, actually.
Oh. The Transiting Exoplanet Sky Survey?
No.
Okay,
that's different. Yeah, this is
Transiting
TES.
Exoplanet Survey Satellite. I always get that one wrong. That's really cool. I really like that your projects sort of have all these transferable skills. I think that's a really nice way to have a PhD. Is there anything else about your research that you would like to share with our audience?
Well, I can talk about sort of the one that I'm in the thick of right now, because we were working on a proposal that is sort of still in progress. I'm not going to talk about it too much, but
the NDA of it all.
The NDA of it all. We're very interested in the way that we can detect hydrogen, obviously on the lunar surface, but with specifically gamma rays.
Yeah.
And the reason for that is because, you know, you have the moon in space, and you have all of these protons hitting the surface of the moon.
Where are these protons coming from?
These protons are just in space,
so if you're just in space, you're also getting blasted with protons.
Yes.
Oh, that's really funny. Okay, I didn't know that.
So galactic cosmic rays are 90% protons and 10% alpha particles, I'd say.
Yeah.
And then some, you know, small particles like helions and stuff like that. But mostly protons that, because the moon doesn't have an atmosphere, very easily bombards the surface of the moon, which we cannot see with the naked eye, but we can see in the gamma spectrum, because when the materials in the lunar surface interact with the protons, they gain energy and have to release that energy somehow. And a lot of the materials will release it in the gamma energy spectrum. And so we can have, you know, a spacecraft that orbits and detects these gamma rays, and hydrogen has a characteristic gamma ray at 2.2 mega electron volts. And so if we see a 2.2 mega electron volt signature, it has to be hydrogen.
Yeah.
So it's a very surefire way of detecting hydrogen on the lunar surface, and that is one of my projects, is to try and map hydrogen using gamma ray spectroscopy.
I can't believe you have 3 projects and they are all like so cool. I feel like when people have 3 projects, usually like one of them's a dud. But this is the project I came up with when I was an undergrad, and I accidentally like wrote an entire peer-reviewed paper in my geophysics class. And then there's spiders on Mars. Who doesn't love spiders on Mars? And there's gamma rays. Everybody loves gamma rays too.
Actually, the peer-reviewed paper that I accidentally came up with was a separate project than the rock abundance one.
Oh
but
my gosh.
I appreciate the flattery. That's very...
I'm trying my best.
No, you're good. I have had a lot of, like I said, side quests thanks to Dave, which sometimes gets me down because I feel like I go slower than most, but then I have to remind myself that I actually have a lot of skills that
Well, I feel like what's funny about grad school is you sort of become a smaller version of your advisor to some extent. Like, you learn a lot about how they became a professor, because all advisors are successful people. They became professors at some kind of institution, which is very impressive. And so you sort of like pick up these skills from them. And I see that what you have from Dave is the side quests.
Yeah.
And the childlike wonder.
That's true, hopefully.
You probably just already had that.
Oh, that's so sweet. That's the greatest compliment anyone can give me. Honestly, sometimes I feel like I've lost my childlike wonder, but then, my therapists tell me that I need to find it again.
Well, I mean, you definitely still have it when it comes to your research. I can hear it in the way that you talk about it.
Oh, I'm glad.
I mean, other people, when they tell me about their research, it's like, this is a drag and this one's boring. But this is like, all of these are fun and cool, novel ideas, and like so much cool science that can be done with sort of like what I would call relatively limited engineering. Like, you're not having rocks flown back. Like, this is just infrared cameras, which is like very regular technology that we have on Earth. But when you apply them to nearby bodies, you can learn so much about geological processes, not only about the moon and Mars, but about other things too.
Yeah. And the really fun thing that is one of my favorite parts of the job that I don't get to do as much anymore because I've sort of transferred into remote sensing, which is basically just sensing objects not on Earth, basically, and through remote methods that are not manned and not controlled. But I love going into the field and doing Earth analog stuff. Yeah. So what that means is we basically study features on Earth that might be similar to features that we're looking at or interested in on the moon or Mars. So, for instance, a lot of the pyroclastics and volcanic deposits in California, Southern California, right in our backyard, is very akin to some of the pyroclastics that we see in Hawaii and on the moon. So we have a lot of actually researchers who want to go to Hawaii to study the lava flows there because they're very similar to the lunar mare. And it can tell us a lot about, how those rocks formed.
I am also a researcher who wants to go to Hawaii. I understand.
It's so fun to be able to travel to all these places just for science and be like, I can camp out in the wilderness for an entire week because I need to collect data that's going to help me with my research. That's one of the most, I think, fun and exciting things about my job is that I get to do this.
I'm very happy for you. Where can people follow along with your research or with your grad school journey?
You can connect with me on LinkedIn.
Okay.
Or
in order to spell your name out for us really quick?
Yes. So it is Jaahnavee as in Victor EE. That's Jaahnavee. My parents really put in a lot of letters there because apparently some guy told them that it would make me very smart, and
I think it worked. Also, your first name is longer than my first name and last name combined.
Yeah, my whole name is 20 letters.
That's
Thank
incredible.
God I don't have a middle name. But you can also check me out on my website. It is jvenkatraman.github.io, which Venkatraman is spelled VENKATRAMAN. Sorry for that, listeners.
No, I think it's fun. I love celebrating the ethnic names of all of our DJs who come on.
Thank you.
I think it's like really nice, and this is a space where I will learn how to say everybody's ethnic name. I am not going to shorten anything.
I appreciate that.
Anyway, thank you so much for coming on. Any final words for our listeners? Anything you want them to remember?
I mean, I think if you're on the edge and you're sort of considering whether or not you want to get a PhD, and this is, planetary science is something you've been thinking about, but you're not sure, or maybe you didn't even know that it existed, and hopefully now you know it does.
Yeah.
Come to the EPSS department at UCLA and talk to us, or come to EYU. We'll have a booth there. It's called Diviner, the Moon and Infrared.
The Moon and Infrared.
And, we are so happy to talk to anyone who is open and willing to learn about the moon.
Well, thank you so much for joining us today.
Thank you for having me.
This is DJ Stellar Cloud and
DJ Stats Sleuth.
With that, never stop exploring.